And for the next talk, we have Gabe Udell, who is telling us about interpolating between ordinary and bumpless pipe dreams with hybrid pipe dreams.
Hello. I will be talking about exactly that. So, all right, so an outline of what we're going to do. First, we'll talk very briefly about Schubert polynomials. Oh gosh, the orientation matters here a lot. Then we'll talk about pipe dreams, bumpless pipe dreams, and hybrid pipe dreams. So each of these is a way to compute Schubert polynomials. So you want to write your Schubert polynomial down in terms of monomials, and each of these is a way to do that. So pipe dreams are medium old, bumpless pipe dreams are not as old, and hybrid pipe dreams are new. So pipe dreams and bumpless pipe dreams work very similarly. So it makes us want to know how exactly do we connect these and how do we think about the connection. And hybrid pipe dreams are one way to think about this connection. And in the latter part of the talk, we'll talk about bijections between pipe dreams and bumpless pipe dreams, using hybrid pipe dreams and not using hybrid pipe dreams. So Schubert polynomials are polynomials. The double Schubert polynomial is a polynomial in variables x1 through xn and y1 through yn. And the single Schubert polynomial is just in these x variables, and it's what you get by taking the double Schubert polynomial and plugging in zeros for the y variables. And these single Schubert polynomials have positive integer coefficients, and the double ones almost do, but there's some negatives, but they're not that scary. The Schubert polynomials give us this nice basis, and they include the Schur polynomials. And this is not really a very geometry-focused talk, but maybe every once in a while I'll say the word equivariant. And if I say the word equivariant, what I mean is I'm talking about double Schubert polynomials and not single Schubert polynomials. And that's all that means in this talk. So in each of these sections, when we talk about pipe dreams, bumpless pipe dreams, and hybrid pipe dreams, we're going to do it by examples. So here's a bunch of examples of pipe dreams, and let's see what we observe. So in each of these, we got a 3 connected by a pipe to a 3, and a 5 connects to a 5, and always I connects to I. In none of these are we seeing 2 pipes crossing twice. I'll explain that again in a moment. We've got these pipes all going from the tops to the lefts. Our left sides of these things are labeled from the top to the bottom, 1 through n, and the tops have some funny order. In the conventions in this talk, that order is going to be given by the inverse of a permutation. So we'll have some permutation pi, and we'll write pi inverse of 1, pi inverse of 2, and then pi inverse of 3, and keep going to label the top. Here's some things which I'm not going to call pipe dreams. Some of these are called pipe dreams in other contexts. So we're not going to allow the 2 pipe and the 3 pipe to cross in 2 different spots. We're going to have pipes in every place. We won't have pipes connecting that edge and that edge, or random pipes like that. And here's another example of 2 pipes crossing twice, but it's a little harder to see. So here's all the things that I just said, but written in words instead of pictures. So these are the tiles that we're going to allow in our pipe dreams. We're going to fill out this thing to connect to the top to the left. We're not going to use vertical tiles. Pipes don't cross twice. Each pipe connects I on the top to I on the left, and we'll label with the inverse permutation. So one thing that's weird about this is some of these tiles don't get used. You can prove that given this definition, the horizontal is never used, and that's why it's never in the definition anywhere else that you read the definition of a pipe dream. We need it for later. So here's some other properties that you can prove based on this setup. And here is, on this slide, is how we'll compute Schubert polynomials using pipe dreams. So we'll call the set of pipe dreams for pi PD of pi, and we'll define this weighty set, which is going to tell you where all of the weighty tiles, where our weighty tiles are crosses and horizontals. And we'll note the label of the row and the physical column position. So given this, we can compute our double Schubert polynomials. We'll sum over all the pipe dreams, then we'll product over all the weighty tiles, taking this term x sub row label minus y sub column position. And this gives us the double Schubert polynomial. So now we're going to do bumpless pipe dreams. If you've seen bumpless pipe dreams before, you might look at this and say, oh, that's upside down. Yes, it is upside down. I won't say they're upside down bumpless pipe dreams. I'll just say they're bumpless pipe dreams. We also kind of need to turn them upside down to make them compatible with our later definition. So here's a bunch of examples. They're similar to our pipe dreams. We connect I on the top to I on the right. We label the top with the inverse of a permutation. We're not having two pipes crossing twice. Now we've kind of changed our shading convention. Earlier we were shading these horizontals and crosses because those were what were giving us weights. Now blanks give us weights, so we shade those in. And the numbering's a little different. The rows are now numbered 1 through n, starting from the bottom rather than starting from the top. So here's some of that written in words. These are the tiles that we're going to allow, and we're not going to allow this hyperbola-like thing that we call a bump. And pipes don't cross twice. We connect I to I. We label with an inverse. And we label the right edges 1 to n in an order. So it's a little similar to pipe dream, but a little bit different. And we have an extremely similar formula. So this is how we're computing the double Schubert polynomials. We're summing over our bumpless pipe dreams and then producting over our weighty tiles. And this is x sub the label of the row minus y sub the position of the column. So we're not looking at the label on top of the column. We're looking at where it is left to right. And these formulas are so similar that we really want a way to understand pipe dreams and bumpless pipe dreams in one go. We want to understand why are these two different objects giving us almost the same exact formula for Schubert polynomials. So now onto hybrid pipe dreams. So these are hybrid pipe dreams, and the idea of a hybrid pipe dream is that some rows are going to be ordinary pipe dream rows, and some rows are bumpless pipe dream rows. And we'll alternate between these in whatever fashion we want. So we could have bumpless, 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 ordinary, 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 or ordinary, 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 bumpless, 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 or ordinary, bumpless, ordinary, bumpless, ordinary. So our ordinary rows have a number on the left, and our pipes are moving down and left, and our bumpless rows have a number on the right, and our pipes are moving down and right. And I probably did the wrong hand motions because I'm facing you. Also, pipe dreams and bumpless pipe dreams are both types of hybrid pipe dreams. It's just a pipe dream where all the rows are ordinary rows or all the rows are bumpless rows. So here's all that now in words, where these are ordinary tiles, those are bumpless tiles. Each row is either ordinary or bumpless, and pipes are connecting the top to the left and right, and no two pipes are crossing twice. So it's a little bit dense in this slide, but it's okay. It's ideas which you would sort of guess you need to define after a few minutes. We need to be able to talk about the type of the hybrid pipe dream, which says which rows are ordinary, which rows are bumpless. We have a weird labeling scheme. This is kind of one of the weirder things about this definition. The way it goes is we first label our ordinary rows starting from the top, then we'll label our bumpless rows starting from the bottom, and we'll go like 1, 2, 3, 4, 5 up to n. And it's sort of going in this direction. We say that a hybrid pipe dream is for the permutation pi if it's got pi inverse on the top. And HPD of pi tau is going to be all the hybrid pipe dreams for pi with type tau. So here's a bunch of hybrid pipe dreams with their types alongside them. There's not so much new information on this slide, just examples. And we can kind of start to see how this might help us think about going between ordinary pipe dreams and bumpless pipe dreams, because we have all these things in the middle. Also, a silly weirdness about this permutation is self-inverse, so this is the inverse of 1, 3, 2 on the top. Yeah, so just one quick example. OBO means ordinary, bumpless, ordinary, and we have an ordinary thing where things go to the left, bumpless row where things go to the right, and ordinary row where things go to the left. And our shaded things are what we're calling weighty tiles, where we've got blanks in bumpless rows and horizontals and crosses in ordinary rows. Okay, so now our definition of the weighty tiles, or weighty positions really, is a little more complicated, because for the first time, the labels on our rows aren't in order. We've kind of scrambled them by having both ordinary and bumpless rows. So now it really matters that we have row labels and column positions. Other than that, our way of computing Schubert polynomials is pretty much the same. We sum over all of the hybrid pipe dreams with a given type, and then we product over the weighty positions, taking x sub I minus y sub j. So we've gone from having 2 different formulas for Schubert polynomials to 2 to the n formulas for Schubert polynomials, which is kind of neat. And the hope, the dream here is that these help us connect the 2 ideas and help us interpolate between them. Some tasks are like easier to understand with ordinary pipe dreams, and some are easier to understand with bumpless pipe dreams. The hope is maybe some tasks will be easier to understand with things in the middle, or we'll be able to translate our understanding on one side to the other in a gradual fashion. All right, so double Schubert polynomials are great, and I think that's what I think of as being at the heart of this work. The story really works for double Schubert polynomials, but we don't have that much time, so we're going to talk about single Schubert polynomials. We're going to do that by defining the x monomial and the y monomial associated with a hybrid pipe dream. And we get these by taking this weight that we associated with a hybrid pipe dream and plugging in zeros for the x's or plugging in zeros for the y's. So we get the product of x's for the weighty tiles or the product of the y's for the weighty tiles. And this keeps track of rows and this keeps track of columns. And using either of these, we can compute the Schubert polynomial. This is just saying that transposing a pipe dream or a bumpless pipe dream switches rows and columns and switches a permutation for its inverse. So we can use our y weights to think about Schubert polynomials just as easily as the x weights, and we can go between these things by transposing. Okay, so this slide is not designed to help you understand Monk's rule if you've never seen it before. That is not the purpose here. I want you to know Monk's rule is an important formula. And I want you to see this formula and say, oh, we have a Schubert polynomial, a bunch of Schubert polynomials, and a bunch of Schubert polynomials. And you should think, hey, that's a bunch of pipe dreams and another bunch of pipe dreams. Or, hey, that's a bunch of bumpless pipe dreams and another bunch of bumpless pipe dreams. So a combinatorial proof of this formula looks like a map which sends pipe dreams on the left-hand side to pipe dreams on the right-hand side, or bumpless pipe dreams on the left-hand side to bumpless pipe dreams on the right-hand side. And these proofs have been done. A note on this second one, so I think a combinatorial proof of Monk's rule first was done by Bergeron and Billy in a slightly different way. And I think maybe some of the idea around this proof was also arrived at by Book, and I don't know the exact history there. Just that it's more complicated than what's on the slide. Okay, so why did I go on this tangent about Monk's rule? We were talking about hybrid pipe dreams and like bijections maybe. So the reason is because of this Gauhong bijection, which gives us a bijection between bumpless pipe dreams and pipe dreams. This has been done, and it's wonderful. And it preserves the x monomial. So that means that it demonstrates the combinatorial equivalence of our 2 formulas for the single Schubert polynomial, the one formula in terms of pipe dreams and the other formula in terms of bumpless pipe dreams. This is in the literature, and it's great. And even greater is it's canonical in a sense. Or I think it's very canonical, actually, in more than one sense. So we talked about Monk's rule being proven combinatorially by these maps from pipe dreams on the left to pipe dreams on the right, or bumpless pipe dreams on the left to bumpless pipe dreams on the right. And these maps commute with this bijection. And in fact, any bijection which commutes with these maps is the same bijection. There's only one that has this property. So this is great. Okay, so now that we have this in our toolkit, we can go back to hybrid pipe dreams and see what they can tell us. So a note on this, we're preserving the x monomials here. So we're proving something about single Schubert polynomials. And there is a sense in which you can't do better. Like you can't really have a weight-preserving bijection showing the double Schubert polynomials are equivalent. Despite that, there's some funky things you can do which actually do allow you to show the combinatorial equivalence, or to combinatorially show the equivalence of our two formulas for double Schubert polynomials using pipe dreams or bumpless pipe dreams. And there's not quite time to talk about it. But know that that's there, and we're going to talk about some special cases. So special case 1 is we decide to only focus on these x weights, only focus on mon x. We'll preserve that, and then we can construct bijections between any two types of hybrid pipe dreams that preserve that, and show the equivalence of those formulas for Schubert polynomials. And also, we can choose to preserve the y monomials. So a work in progress that's like 97% done is that this bijection, which preserves x weights, is the same as the Gao-Huang bijection. So going through the hybrid pipe dreams using these objects to understand the connection, we get the same bijection. Yeah, and for the next couple slides, we're going to talk a little bit more about phi y than phi x, because it's a little easier to understand, but things work similarly. All right, so we're going to have two steps. Step 1, we're going to switch the last row. We'll change the last row in a hybrid pipe dream from being ordinary to being bumpless, and we won't mess with any other rows. So so we're talking about how are we going to connect different types of hybrid pipe dreams, and this is our first part. Our second part is we're going to figure out how to swap adjacent rows. So we have an ordinary row on top of a bumpless row, and then we'll change that to being a bumpless row on top of an ordinary row by modifying those two rows and not touching any other rows. And at the bottom of the screen there, we have sort of an example of how these two types of maps allow us to go between all ordinary and all bumpless. All right, so here's how we switch the last row. There's really only one way to do this. You take your horizontals, you turn them to blanks, you take your blanks, you turn them to horizontals. A piece that turned you left now turns you right. That's how it's going to go. When you want to switch to adjacent rows, it's a little more complicated, and the rule is not going to be clear from these pictures. But what I want to be clear is what we're doing. We're taking these two rows and changing them so the ordinary row that was on top now is on bottom, and the bumpless row that was below now is on top. So this is the type of thing that we're going to do. And here's how we do it. There's a bunch of local rules. So these are like a bunch of little dominoes that can appear in your pair of rows. So for example, over here, we've got a cross on top of a vertical. So we look at our rules and we say, oh, there's cross on top of a vertical. That should become vertical on top of a cross. And indeed, that's what it becomes. So we're like applying all these little local rules. And oh, yeah?
Sorry, just a quick question. When you have the numbers on the bottom, is this shorthand for something?
Yes, sorry. So here we're just labeling the pipes. And over here we're labeling the pipes, but we're only using like 0, well, no, I think we're only using 1 and 2 and 0 in one case. The point here is just to distinguish which pipes are different from each other. So I said it's this nice local rule, and I was like a little bit lying. It's mostly a nice local rule, but you need to know which pipes are different from each other. So this information is just telling you, over here, is this one pipe the same as this one pipe, or is it this situation where these are two different pipes? And those numbers come from where did they start on the outside of the pipe dream. You have the pipe connecting 1 to 1, and that's the one pipe. But like these numbers aren't important, they're just saying which are different. Did that make sense? Okay.
And then for the upper right, is that supposed to be a 2 on top?
Oh, that is supposed to be a 2. That's a good catch. Yes. Okay. Yeah. So these rules look complicated. They're a lot less complicated than they look. There's 23 of them here. You can boil them down to 3 relatively simple rules by just looking at the numbers that appear on the edge. And it turns out the numbers appearing on the edge of a domino determine what domino that is. This slide is to say that having this bijection, which preserves y weights, actually you can make a bijection which preserves x weights. And mostly done, but slightly less done than the previous results, this is also the same as the bijection preserving x weights that we got by swapping rows, and it's the same as the Gao-Huang bijection. where are we at? So I'm mostly out of time. These slides are to talk very briefly, but we're not really going to go into it, about the kind of machinery that we use to show the equivalence of our formulas for double Schubert polynomials. Before I end, I want to say that there's a lot of further questions, and I hope not to answer all of them on my own. So I think two of the more important ones in my mind are describing Monk's rule maps, so recombinatorially proving Monk's rule using each type of hybrid pipe dream. And also, now we have this bijection between these decorated objects that I didn't get to talk about too much on the pipe dream side and the bumpless pipe dream side by going through these decorated hybrid pipe dreams. But this makes us want to know, how can we do this without using hybrid pipe dreams? So the Gao-Huang bijection didn't use hybrid pipe dreams, so we should be able to soup up the Gao-Huang bijection to something on decorated things that also doesn't use hybrid pipe dreams. So I'm interested in these two questions. If you're also interested, talk to me sometime. So I'm thankful for many people, many of whom are not listed here, but this is a start. And I'm also thankful to all of you for listening for the last 20 minutes.
Let's the questioning begin.
Oh.
Is there a version of hybrid pipe dreams which is more symmetric in the rules of rows and columns?
So you asked, is there a version of hybrid pipe dreams that's more symmetric in the rules of rows and columns? I'm not sure that I understand the question. I think
The symmetry between the x and the y variables. So is there a version of hybrid pipe dreams which more explicitly exhibits that?
so. I think my answer is some combination of no, I don't know, and I don't understand the question. But I can say that there is sort of like another option for how we're going to do this. So hold on. Got to find the hybrid slide. All right. So we chose to start messing with the rows here. We could have started messing with the columns. So instead of doing what we did, where some rows are ordinary and some columns are ordinary, we could have had some rows are ordinary, some rows are bumpless. We could have had some columns are ordinary and some columns are bumpless. And then if we did that, then the thing which is now our y weight preserving bijection would be the x weight preserving bijection.
Okay, but can you do both?
What do you mean? So sorry, you asked, can you do both? I'm asking, what do you mean by that?
Mess with both rows and columns.
I don't know. I've been wondering that, though. Yeah. Yeah.
I think you can do both, but I think you can't. I think you can basically dig away from the northwest doing pipe dream stuff and dig away from the southeast doing the bubbles pipe dream stuff. But you'll get things that you can't fit into a n by n grid into an IC picture with pipes. I think that's the basic issue. So you'll get some fairly horrible combinatorial objects, and you'll have to transpose symmetry you're asking about, and then you won't work with it because it's ugly.
Okay, thanks.
So Alan said you can mess with rows and columns at the same time, but it'll be ugly. Yeah.
So maybe you've mentioned this and I missed it, but so you've constructed for every pair of OB words a bijection between the hybrid pipe dreams for that OB word, is that right?
Yes,
Yeah.
with a little bit of wiggliness on the meaning of explicit.
Okay, sure. So do you know if you have tau 1, tau 2, tau 3, you're calling them tau, right? Well, anyway, you have three OB words, and you compose the bijection from the first to the second, and then the second to the third. Do you get the one that you found from the first to the third? Is that something you know about?
Yes, so the question was we have three types of hybrid pipe dreams, and we have a map between this one and the middle one, and the middle one and the third one, and the first one and the third one. If we compose our first two bijections, do we get the third one? And the answer is yes. we're doing one kind of thing between any two pairs, and any way of composing things is giving us the same idea. Yeah?
So when you are switching either the last row or to adjacent row, at any point is there like the danger of creating two pipes crossing more than once?
No. But part of me wishes there was, because I don't know how to extend things into K-theory at the moment, and I don't know. But no. Yeah, so when the last row always looks like this, where there's only one pipe appearing in the last row, and it just swoops to the left or swoops to the right. And so there's no other pipe that's going to come and cross it. I guess just when the rules are described like this, it isn't necessarily clear that you don't have pipes crossing twice. But yeah, I think because these are designed so that the start of a pipe and the end of the pipe in these two rows aren't changing. There's like you could make a sort of like topology in the plane argument that if two things cross, they still cross, and if two things don't cross, well, like, I guess you have to check the rules that they don't cross now, but if you went from not crossing to crossing, you'd actually have to cross twice, and so it would be a very, like, local problem.
So I guess if you're switching non-adjacent rows, it wouldn't be as nice.
Yeah, so the way that we switch non-adjacent rows is just by switching adjacent rows lots of times. So if you're switching non-adjacent rows, something much more complicated happens.
All right, so I think we are out of time for questions. So please stick around because we will have a Georgia Brancart tribute talk by Tom Halverson. So.